Welcome to the deep dive. We take the complicated, the revolutionary, and the frankly staggering pile of sources you send us and distill it all down.
And today, we are diving deep into a subject so transformative it won the Nobel Prize in chemistry in, well, record time. We're talking about the gene editing system CRISPR-Cas9.
And this is so much more than just a scientific breakthrough, right? It's
hmm
arguably the moment humanity stopped being, a passenger in evolution and actually took the wheel.
It really is. Our sources, from academic papers to Walter Isaacson's fantastic book, The Code Breaker, they lay out this story of genius, of fierce competition, and just unprecedented ethical challenges.
So our mission is pretty huge.
All right.
We need to unpack the journey of the pioneers, especially Jennifer Doudna, understand the incredible speed of this technology, and then confront this ethical tightrope we're now all walking.
The challenge for you and for us is just keeping pace. The science is moving so fast that our moral frameworks, they're just struggling to keep up.
Okay, let's unpack this. Before we even get into the Nobel timeline, for anyone who might only know the acronym, what does CRISPR-Cas9 actually do? Is it really like a genetic find and replace?
That is the perfect analogy. And it's that simplicity, that function, that makes it so incredibly powerful.
Right.
Think of DNA as this impossibly long instruction manual. Before CRISPR, if you wanted to change one single word in it, you basically had to try and rewrite the whole chapter blindfolded.
The hugely inefficient process.
Exactly. CRISPR changes all of that. The Cas9 enzyme that acts as the molecular scissors, and the CRISPR RNA is like the guide, the GPS system, that finds a specific tiny sequence in all that code.
So it guides the scissors right to the mistake.
It guides them right to the error, lets scientists snip out the bad code, and then potentially replace it with corrected code. That precise cut and paste function is why it just exploded.
And when you say exploded, you mean history-making speed. I mean, how did a discovery with its first major publication in 2012 go from a lab bench to Nobel Gold in 2020? 8 years. That's stunning.
It is stunning. When you compare it to foundational work that took, decades to get recognized, it just highlights the immediate impact.
Like what?
Well, think of Brenner, Sulston, and Horvitz. Their work on the genetics of cell death started back in the 60s, but they didn't get the Nobel until 2002.
That's a 40-year lag.
40 years. And that used to be the norm. We've seen some faster ones, sure. Yamanaka's work was 5 years, graphene was 6. But 8 years for something as vast as genome editing, it just speaks volumes.
And what's fascinating here is that the prize was awarded to Jennifer Doudna and Emmanuel Charpentier, even while all these intense patent battles were still raging.
Oh, absolutely. And before the biggest ethical questions had even begun to be properly debated on a global scale, the technology just became a staple tool instantly.
Which brings up a really interesting debate we saw in the sources, a sort of internal scientific argument about the scope of the discovery.
Right.
Should a tool like CRISPR be celebrated as much as, say, a foundational discovery like G-protein coupled receptors, GPCRs?
This is a classic scientific disagreement. Foundational knowledge versus applied power. For anyone unfamiliar, GPCRs are like the cell's mailboxes. They sit on the outside, receive signals, and then trigger huge changes inside.
And they're critical. I mean, something like 30 to 50% of all modern drugs target them.
Exactly. So the argument for GPCRs is that they revealed this massive biological mechanism we didn't even know existed. They showed us fundamental doors.
But the CRISPR argument is different.
The counter-argument, and the one that seemed to sway the Nobel Committee, is that while GPCRs are a discovery of one critical process, CRISPR is a technology that lets us make countless other discoveries.
It's the difference between discovering a new law of physics and inventing the telescope that lets you see 1,000 new worlds.
That's it. You can use CRISPR to study GPCRs or cancer or anything. Its utility is universal across all of biology, and that's why labs adopted it overnight.
But speaking of that, of the collective nature of discovery, we have to mention that the Nobel, well, it didn't capture every single contributor, which really speaks to the messy reality of scientific credit.
It does. I mean, the sources point to the Lithuanian scientist Virginijus Sikenis. He was instrumental. He won the Kavli Prize with Doudna and Charpentier, but his foundational paper, it was initially rejected by top journals.
That complexity really sets the stage for Jennifer Doudna's story.
Absolutely. The Code Breaker details her origin story, and it's just defined by persistence. She grew up in Hilo, Hawaii, and as a 6th grader read The Double Helix.
Watson's account of discovering DNA.
And that book just set her life's ambition.
But she was met with this incredible bias.
Outright bias. Her high school guidance counselor told her point blank, Girls don't do science.
It's hard to imagine hearing that.
And then going on to get a PhD from Harvard and change biology forever. And even in her early professional career, she was often barred from the male-dominated clubs working on the Human Genome Project.
So she took a different path?
She did. She partnered with other leading women to study RNA structure instead.
And that collaboration with Charpentier, the one that led to the 2012 paper, it was so international. A French professor, students from Poland, Germany, the Czech Republic, and Doudna in Berkeley.
That synergy was incredible. But what came next was this white-hot rivalry.
The race.
The race.
Yeah.
Starting in 2012 between Doudna's team at UC Berkeley and Feng Zhang's team at MIT and Harvard, they were both racing to be the first to prove that CRISPR could edit human DNA.
The competition must have been just grueling.
Fierce. I mean, it fueled these massive, rapid breakthroughs, but it also instantly devolved into huge patent battles between the institutions, billions in licensing revenue on the line.
And that dynamic, you see it all the time in science. But this is where the story gets really, really interesting. Because when this massive shared threat of the COVID-19 pandemic hit,
everything changed.
That competition just paused.
Yeah. It was a pivotal moment. For years, Doudna and Zhang were locked in this high-stakes patent war. But when COVID hit, they literally stopped their battle and started working together.
They used their expertise to work on the virus.
Immediately. They pivoted to creating novel, rapid diagnostic tests. They realized the tools they had developed needed to be applied to save lives. That shared threat just transcended everything.
It's a powerful story. But of course, no discovery happens in a vacuum. We have to remember the foundation this was all built on.
Absolutely. I mean, you have to give a debt to Francisco Mujica, a Spanish scientist who, way back in the 90s, first spotted these strange, repetitive DNA sequences in bacteria.
Which he named CRISPR.
He named it CRISPR. He had no idea what it did, just that it was there.
And my favorite part of the origin story, the yogurt.
The French food scientists in 2007, they figured out CRISPR was actually an immune system. The bacteria used it to vaccinate themselves against viruses, and by doing that, they basically secured the future of the global yogurt industry.
It just shows you where these monumental leaps can come from. But now let's move to the societal implications, because the so what for you, the listener, is immediate. It's happening now.
CRISPR has already moved from theory to clinical impact. It's curing people.
Curing them.
Yes. The sources document cases where it's been used to cure individuals with diseases like sickle cell and beta thalassemia. We're talking about fixing the broken cord that causes a lifetime of suffering.
And the trials are accelerating.
Right.
We've seen results from a trial for end-stage GI cancer patients where one patient had a complete response. The tumors just vanished for over 2 years.
And it's being explored for HIV, and looking ahead, the power only increases. We're moving beyond single-letter edits. New systems are being developed that could insert entire corrected genes.
Which would be a one-time fix for dozens of genetic illnesses.
Exactly. And this isn't just about human health. The implications for the entire planet are massive.
You mean things like agriculture?
Think about it. We can edit crops to withstand climate change. We can edit mosquitoes so they can't spread malaria. There's even this idea of community editing, modifying genes across whole ecosystems.
And that power, that ability to edit life itself, pushes us straight into ethical quicksand. We have the tool, but do we have the wisdom?
This is where the designer baby debate comes roaring in. If we can eliminate a disease, should parents also be able to choose non-medical things? Hair color, height, muscle mass.
And where do you draw the line on what you're willing to edit out? It's one thing to talk about physical diseases, but what about conditions like autism or bipolar disorder or depression?
Are those flaws to be eliminated? Or are they just part of the complex human experience? That line is perilously thin.
It reminds me of that moment in the source material where Doudna herself was confronted by the dark side of her own creation.
The nightmare.
The nightmare.
She dreamt she was approached by Adolf Hitler, who was keenly interested in her technology. And that nightmare for her, it solidified this realization. Creating a powerful tool is only half the battle. You have to actively prevent its misuse.
Which raises another huge question.
Yeah.
Social inequality. If this is an expensive technology and wealthy parents get access first, could you literally encode inequality into our heredity?
That's the chilling prospect, creating a biological aristocracy, where you're not just born into wealth, you're born with, genetic advantages.
It forces you to look back at how other genetic pioneers handled this gravity. The sources mention James Watson, co-discoverer of DNA.
And how later in life he was banned from a scientific meeting for his scientifically unfounded and racist views on intelligence. A really narrow view of genetic potential.
But the powerful counterpoint came from his own son, Rufus, who suffered from schizophrenia.
And Rufus observed that his father's statements represented a rather narrow interpretation of genetic destiny.
The irony is just profound. The man who unlocked heredity had this narrow view, but his son, living with a genetic condition, had the wisdom.
It's a necessary perspective. I mean, we've seen the incredible speed of CRISPR's recognition, highlighting its power, but the scientific debate is now completely, utterly inseparable from the ethical one.
And the history of CRISPR is still being written. For the first time, we have the tools to potentially edit out things that we've always considered part of being human. So if knowledge is most valuable when it's applied, what is our responsibility?
What is our responsibility when the application fundamentally changes what it means to be human? Should we just focus on eliminating what we see as flaws? Or is there a wisdom we risk losing when we assume total control over our own genetic destiny?
That's the ultimate question we'll leave with you today.